Zbigniew Jelonek, Professor Zbigniew Jelonek from the Institute of Mathematics, Polish Academy of Science, Poland, with the talk Whitney theorem for complex polynomial mappings. Please share your presentation.
And also, please turn off your microphone.
Do you hear me?
Yes.
Yes.
Okay. Now probably it's working. I'm sorry. It's my pleasure to be here and to thank you very much for the invitation. And I would like to say a few words about algebraic version of famous Whitney theorem about mapping of the planes. In fact, I say something in the more general setting. We create some framework to study topology of general polynomial mappings, yes? Because maybe it is not well known, maybe the people are not aware of this situation that classical Whitney and Thom theorem are useless if you would like to study generic polynomial mappings, yes? Because Thom-Whitney methods is based on the Whitney topology, and Whitney topology is discrete in the set of polynomial mappings, yes? And in fact, these theorems are not true if we restrict to polynomial mappings, yes, okay? Polynomial mappings are the most classical objects in complex analysis, but the topology has not been studied up till now. Yes, in fact, we studied only function. Nobody studied mappings. Yes, and I would like to give the first approach to how to do this. Here we describe an idea of such a study. We consider the family omega Cn d1 dn of polynomial mappings of this type, yes, where components are, the degree of components are bounded by the number d1, dm respectively, okay? And the same we can do in some more general setting, yes. If we have a smooth subvariety of Cn, we can also consider the analogous family of polynomial mappings. If m, x, y are affine irreducible varieties, and phi is an algebraic family of polynomial mappings, such that the generic element of this family is proper, then two generic members of this family are topologically equivalent, which follows, for example, with my paper from 2017. In the case of Cn, it also follows from Warchenko paper, famous Warchenko paper, yes, in more general even settings, without any restriction. In particular, if x is of dimension n and m greater or equal to n, then any two generic members of this family are topologically equivalent. Yes, for Cn, it is true in more general setting by Warchenko theorem. This is interesting for us. If x is a smooth surface, then the numbers cx and of cusp and dx of double folds respectively for generic family are well defined, and of course it's a natural question how to compute these elements for arbitrary smooth surface. Yes? However, for arbitrary smooth surface it is rather difficult. Then we restrict here only for C2 and for the sphere. For some reasons, for C2 and for the sphere, this is easier because we have a large group of symmetry in these objects, okay? Now, our aim is to describe effectively the topology of such a generic mappings in the case of C2 and the sphere S. However, we introduce some tools which are which are convenient for study of general polynomial mappings from Cn to Cm. Yes, that in fact we study some, we pose some very general theorem which cover almost all situations. Yes, however, we apply this very general theorem only to these two cases. Yes, maybe to explain our methods, because in fact we need here some new tools. Yes, it is not possible to use classical theorems of Whitney and Tom for many reasons. I explain why, but here we have non-proper case. Yes, and in fact an algebraic case. Yes. For Whitney Tom methods are not good for algebraic case for these reasons, that the Whitney topology is not convenient to study algebraic cases. This Whitney topology is discrete on this object. By Jx Cn Cm we denote the space of Q-jets of polynomial mappings. Yes. And the same meaning has this space, JQXCM. And this space has always structure of smooth algebraic manifold. It can be proved in easy way. Now we have to introduce some notion. I'm sorry for these technical details. However, to explain our main theorem, we need this. Yes, this is the space of multijets. To explain the space of multijets, it's simply multijets is the collection of jets in different points. Yes, that we choose a different collection of points x1, xs, and we consider the jet space in every of these points, and this collection is a multijets, more or less. Yes, and this is explained here. Yes, and maybe, okay. And also we say something about Tom-Boardman singularities. If F is one generic mappings, then this space sigma RF of space X that current DXF equal R is smooth, and we can consider the set sigma RS when where the map drops rank S. If sigma RS is smooth, we can continuing. In particular, if n equal 2, we have that sigma 1f is the set of folds and sigma 1 is the set of cusps. Yes, this means that we consider we consider the space at which the mapping, for example, drops by 1. This is a part of the critical varieties. Then again, we do the same. For example, again by 1 and so on. And for generic mappings, this procedure is well defined, which was proved by Boardman. In fact, we have the following theorem. For every sequence of integers, one can define a smooth algebraic subvariety in the space of multijets, such that the JLF, this space, this jet mapping is transversal, such that if this jet mapping is transversal to all submanifolds, sigma 1, sigma, it should be S here, not L. Sigma S with L less than S, then sigma 1, sigma RF is well defined, and X belongs to this strata if and only if jet space is belong to this Tom-Boardman manifold. Yes, and that. Of course, this is true for arbitrary smooth manifolds. We say that the subvarieties, sigma 1, sigma L are Tom-Boardman strata in the space. Yes, then we have the jet space. And the preimage of this jet space are simply these sets defined here. Yes. We will also use the Tom-Boardman manifolds in the space of multijets. We denote by this delta the set of multijets for which these 2 points coincide, yes, these bad points, yes, these bad jets. And we denote here these multi-dimensional Tom Boardman sets, which are defined in this way. Simply to control not only points, but also control some fibers, yes? If we have a mapping that we have a fiber and we would like to control the whole fiber over these points, to have some description of the topology of this mapping. And again, we have this mapping. Let x1, xs belong to the space xs, which is defined xs minus delta, yes? Let U be an open neighborhood of x and be a holomorphic mapping. Again, we denoted this z by this symbol, and y simply the sequence, the composition of value of the mapping. And again, by JS, JKXYX and JKXYX denote fibers of this fiber bundle over X, over point X and the points XY respectively. And here is a Mather canonical identification. We can identify the tangent space to this fiber as a space of jets on the pullback of tangent band of Y. And this is, I'm sorry for this technical details, but it gives some flavors what we have to do here, and also some notion which we use, unfortunately. Let Mx denotes the ideal in Jx consisting of jets of function which vanish at X. Then with respect to this identification, yes, we have identification of these two spaces. In particular, this tangent space has a structure of a module over the space of jets. And now we need the basic definition of the modular set. All this which I introduce here it has this aim that I would like to use some version of Mather theorem to simply build some theory like Whitney Tom theory, but in the algebraic case. Yes, we would like to simply to construct a algebraic counterpart of Whitney Tom theory. Yes. And this the submanifolds of multi-jet bundle is modular if W is a smooth submanifold and the space tangent space to this fiber over XY under identification under this identification is a submodule of MX. This means that it has algebraic structure, yes? Some extra algebraic structure. And now we have the following result of Mather. Let X be a smooth affine algebraic subvariety and W be a modular submanifold. There exists a Zariski open non-empty subset U in the space of all linear mappings such that every L which belongs to U, for every L which belongs to U, the mapping L is transversal to W. And now we would like to use this theorem to construct this Whitney-Tom counterpart of the theory in algebraic case. And to apply Mather theorem, we need the following theorem, which was first observed in the real case by Ishiki, and we applied this theorem, we generalized this to complex case. Let X be a smooth affine subset of Cn, and W be a modular submanifold of the space of some multijets, and let F be a polynomial mapping. Then there exists a Zariski open non-empty subset U in the space of all linear mappings, such that for every L, the mapping F plus L is transversal to W, yes? That we can simply deform a little the mapping L by adding a linear mapping such that it automatically satisfies this transversality condition. Hello, do you hear me? Hello?
Yes, yes.
Okay.
Yes.
Okay, good. Thank you.
Good.
And now we can state our version of Mother theorem. Yes, this is the basic tool in our study. Yes, let X be a smooth algebraic subvariety of dimension K of Cn, and let W be an algebraic modular submanifold. Then there exists a Zariski open subset U in the space of all polynomial mappings from X of degree bounded by D1, Dm, such that for every F belonging to U, the mapping F is transversal to W. In particular, it holds if we take as W the Tom Boardman manifolds, which are defined before. Yes, this is Tom Boardman manifolds. I'm sorry. These are these manifolds. Yes. In particular, it holds if we take as W the Tom Boardman manifolds in jet space. Consequently, every mapping F belonging to U satisfies the normal crossing condition. Hence, it is a Tom Boardman mapping with a normal crossing property. Yes. Then here we have more or less the same as say Whitney Tom theory, but for polynomial mappings. Yes, we have a polynomial counterpart of this Tom Whitney theorem, and then we can start to study these properties of polynomial mappings using this theorem. This is very general theorem. You can use this, in fact, for in every dimension. Yes. However, of course, to study topology even in dimension 3 is much more difficult than in dimension 2. We have some progress in dimension 3, but it's still not finished yet. We have a lot of results in this case, but it's not finished yet. But I believe that it's possible to finish this program in dimension 3. However, for the higher dimensions, it's really very, very difficult. One of the problems here is that we cannot use some tools as Tom polynomials or something similar. I explain why later. Okay, that. Now here we have very simple. This Tom Boardman the singularities are very simple. In fact, in fact, we have that. We have only two singularities. Yes, it is cusp. Yes, which is given by this equation. Yes, this is every cusp is equivalent to this one by some biholomorphic mapping, and we have also the folds. Yes, that we have very simple here. These simple singularities. Now we have also multi-singularities because the multi-singularities are only two folds. Yes, this means that I don't know. I am afraid to use the blackboard because I am afraid that I would be not in a position to go back. But anyway, this means simply that we have a transversal. If you have maybe it's possible. I don't know. Or maybe it's here. No, maybe it's here. No, I'm sorry. Oh, maybe it's... yeah. Okay, I don't use this. Yes, okay. I'm sorry, it's here. We have this too. I'm sorry, how to... how to... I don't know how to...
Which one would you want to?
I would like to switch off this line.
Oh,
But maybe, okay. I'm sorry because I have something here. I would like to use a pen, but maybe I avoid to use pen. Okay. Okay, and we go here. We have these two definitions of cusp and false and double fault is simply something which means that the discriminant has self-intersection, has transversal self-intersection. Yes? This is a multi-singularities here, and we have the following theorem. By this main theorem, with this modification of mother theorem, we have this simple observation. If X is a smooth affine surface and F is a generic polynomial mapping, then F has only false and simple cusps and two false singularities. It should be, I don't know what it is. I'm sorry. Oh, it's whiteboard. Oh, okay. Now I can, yes. That we have a mapping, yes. Here is, for example, is X is a surface. X is a surface. Here is a generic mappings, yes. Then, of course, the critical set here is smooth. And now, the image of this critical set is a discriminant, and it has only double points as here, and cusps as singularities, yes? And these are cusps, and these are double faults. The geometry of this mapping is the following. If you consider pre-image of these points, it has exactly D points here, yes? D1 multiplying by D, no, it's constant, yes? Here the pre-image is only here, yes? And this is, and of course there are also some good points here of smooth points. And here the situation is that we have 2 points here and here, yes? If we consider this point, yes? And this is this multi-singularity because it has 2 singularities which comes to 1 point, yes? Okay, and now I would like to go again. Oh, it's here, yes. Do you see my paper?
Yes, we can see.
Okay, and that probably I explained what I would like to explain, and we have the following theorem.
Yes, we see. The next.
For a general polynomial mappings from C2 to C2 of degree D1 and D2, the set CF of critical points is a smooth connected curve which is transversal to the line at infinity. But no, this is easy part, of course. The curve CF is topologically equivalent to a sphere with this number of hands and D1 plus D2 minus 2 points removed. The discriminant, this is of a mapping F is a curve birationally equivalent to CF, and it has cusp and nodes as singularities, only cusp and nodes. This is exactly what on the picture, yes? And the number of cusp is given by this number, and the number of faults is given by this number. And note here that we have D, which is greatest common divisor of D1, D2. And this is a hint that you cannot obtain this result using some Chern classes or Tom polynomials, yes? Because Nevertheless, we obtain in this way greatest common divisors of these two numbers. Yes, that this means that we have indeed we need here another techniques, and also this remark shows the same, that the discriminant at infinity in general is not smooth at infinity. Yes. Only in some very particular cases, this discriminant can be smooth at infinity. Yes. In particular, we computed here the delta invariant of this germ at infinity of the discriminant. And you see that in general, there are huge numbers. Yes. This is very, very not singular, not smooth, very, very singular points. Yes, that it is not true that generic mappings in C2 is also generic in P2. Yes, in some sense, it is not true. And the similar result we obtain for the sphere. Yes, of course, it is a question how to do the same result for arbitrary smooth algebraic surface. Yes, no, of course, I believe it's possible. However, it seems to be very, very difficult, because even in our situation, when we use some great large symmetry group of the space C2 or the space S, yes, it was not easy to compute, especially with this number of folds. Yes, it is really not easy. It is technically complicated. And I believe that in the general case, for arbitrary smooth surface, it will be much more complicated. Well, of course, it's possible. Probably we need another new tools, but I don't know how to construct these new tools. Okay. And we have the same, it is not interesting. No, and maybe how to prove theorem A. In fact, there is easy part and difficult part. The easy part is to compute the number of cusps, because the number of cusps we have simply we can write equations. Yes, equations, and we can try to compute. We have two curves. Yes, and we can try to compute. Even three curves. We can try to compute the common numbers of points of intersection of these curves. To do this, of course, we need to control the number of these points. Oh, here we have a description of the number of cusps. Yes, more or less, by these three equations. Yes, and to compute this, we have to know that these curves are nice at infinity, and we have this lemma, three lemmas, yes, which shows that all these curves are nice at infinity. And then if we check this, yes, you'll see that it needs some numbers of lemmas to compute all details, yes. And then finally we can use Bézout theorem in some form to compute this number of cusps precisely. Yes, but this is easier part, but also it needs some computations. It's not very easy. Yes, it's easier but not trivial. Yes. And this is the more difficult part, to compute the number of folds. Yes. In fact, to do this, first of all, from our version of Mother theorem, we have this. Yes, that we have that this mapping has only nodes and cusps as singularities. Yes, because this is simply this normal crossing property assures us that we have only double points here. Okay, and to prove the general to compute the number of folds, we need the theorem of Serre, yes, which shows how to compute how to connect the delta invariance of the curve, of singular point of the curve, the genus of the curve with degree of the curve. Yes. Fortunately, we have this theorem, and then we have also we can compute also the degree of the discriminant. Is not very difficult. Yes, it can be done, and we have also this Milnor method how to compute the delta invariant of the non-singular point on a curve. Yes, and then we can put this together, and we have this theorem which follows from the Serre theorem, and if we are in a position to compute this, then in fact these points at infinity, then in fact we are in a position to compute the number of folds. Yes, because the curve has we know the number of cusps. If we compute this, we know the number of delta invariants at infinity, and the remaining part is only the number of points the number of folds. Oh, probably it should be also false here. Yes, I'm sorry. Because here is all points, also false. Yes, here. Yes. And how to prove this false at infinity? In fact, we did this directly, but of course it's not easy because you have some parametric. Yes, you can do this in the family. Yes, no, but it's possible. Yes, it is. This is the most technical part of our proof. It's complicated. Yes, but however, it can be done. Yes, and finally, we have this result, which I mentioned before. Yes. And there is also a converse result, which is our new result. It's proven by me and Farnik, my former PhD student. And this means that, in fact, the number of cusps and folds determines the topology of the mapping from this family completely. Yes, this means that if a mapping F has maximal number of cusps and maximal number of nodes, then it has a generic topological type. Yes, that to be of a generic topological type in this family means to have maximal number of cusps and nodes. It's not. It is interesting. In particular, the mapping with generic topological type form as a risky open subset in this space. As a corollary, we see that if we have the two mappings from the space of the polynomial mappings omega 2 d1 d2, this means this mapping from C2 to C2 bounded by degree bounded by d1 d2. Under this technical condition, d1, d2 is greater than 2, then if F and G have maximal number of cusps and maximal number of nodes, then they are conjugate by homomorphisms. Yes? That we know that they are automatically conjugate by homomorphisms. There are two homomorphisms from C2 to C2, such that G is composition phi composed by F composed by Psi. The main key to prove this theorem is my theorem with Ding, with Vietnamese, which I prove with cooperation with Vietnamese mathematician Ding about the Tom's stability lemma for non proper mappings. In fact, it can be used here in very nice way. Okay. And I have a few minutes, then I say also some facts, because why I would like to explain, because some application of our theorem, we can here define the notion of generalized cusp in this way that the germ Fa is proper and the critical curve is reduced near A, and the discriminant of Fa is not smooth. Yes, this means I can use this dashboard, yes, but I maybe better not, yes, that. Okay, and we have this first proposition. First of all, and assume that F has a generalized cusp at A. If UA is sufficiently small ball around A, then A, we can introduce the multiplicity of this cusp is equal to the number of sim cusps in UA for general mapping F. This means simply that in some sense, generalized cusp can be obtained from the generic mapping if we pass to the limit, yes? If we have a very close generic mapping to these points, then the number of cusp in the small neighborhood is exactly the multiplicity of this generalized cusp. And here is maybe the most interesting corollary. If F is a generically finite polynomial mapping with reduced critical curve, then it has not more than this number of singular points which are not false. This means that even they have, it can have only this number of isolated critical points. And here the assumption is only this, that this mapping has reduced critical curve. And analogous theorems are true in the case of a complex sphere. I'm sorry, here. This is, I don't know whether I have time. Maybe I finish here, okay, because thank you for the attention.